an example of regression K and N. Here we have total 15 data points. These data points represents the length, the weight of metal rods, and their price or their cost. So the length of the rod, the weight of the rod, and its cost depending on different qualities. And what we have to do is calculate the cost for a rod which is not given within this data set. It's not within this data set. This is a new rod with length of 7 and a weight of 8, and we have to estimate what would be the cost of this rod, metal rod. So as we discussed earlier, first we need to determine the K value. Here we are going to consider K as 3, so we are going to consider 3 nearest neighbor, and what we are going to do is estimate the cost. So the target or the unknown example in this case is the point 7 and 8, where 7 represents the length and 8 represents the weight of the metal rod. So this is our example, and we have to calculate the label, which is the cost. So the first data point that we have here is 10 and 15, and we are going to estimate the distance. And considering the Euclidean distance, we are going to calculate this Euclidean distance. So what we will do is simply the Euclidean distance, and when we estimate this value, it comes out to be 7.61. So we populate with respect to all data points, and the point under consideration is this 7 and 8. So 7 and 8 is your point under consideration, and calculate the distance with all these data points, all of these 5 and 10, estimate, and then it comes out to be 2.82. The first step is select your K and then estimate the distance of all the data points, then arrange them in the point of distance values, increasing value of distance. So the lowest is 1, the data point is 7 and 9. The next is 5 and 8. And the third data point that we have here with the lowest distance is 9 and 7. So we are considering these 3 data points. And since we have chosen the data point 7 and 9, the next is 5 and 8, and the last one is 9 and 7, which has the minimum distance. And we check the value of the cost, which comes out to be 33 from here, 32 from here, and 30 from here. We sum this up, divided by 3, we have 3, and take the average, and this comes out to be 31.67. So the estimated cost of this unknown sample of rod, metal rod, would be, with a length of 7 and weight of 8, would be 31.67. So this is how we can do the regression problem of KNN. So we are actually predicting the value of a numeric value considering the existing values that we have, because this is supervised learning. Okay, so we have studied the effect of choosing the hyperparameter K. So now comes the question. Why are we just counting for classification, averaging for a regression type problem? How about these two scenarios? So if we are choosing a value of k is 5 for these black and red data points, and we select k is 5, so what about this x1? Does this belong to black or red? And we have 5 points, these two red, 3 red and 2 black points. So what does this belong to? Again, in case of x2, if we are considering 5 neighbors in this data, so what does this belong to in this type of problem? And in the case of regression type problem that we have here, we have two classes, 1 and 10, and we have to determine the regression value for x1 and x2. Do we consider x1 if we consider 5 neighbors? Where does this belong to? Does it belong to 1 or 10, this x1 point, and the value at x2 point, does this belong to 10 or 1? So these are some of the values that we can, some of the scenarios in which we can study a variation of our existing KNN algorithm by just not counting or just not considering the average values. So how do we do that? So in this case, you can see the problem here. If we are considering 5 neighbors for x1, although we have only 2 blacks and we have 3 reds, and how do we classify in case of voting? We classify this as red because we are considering 5 values. So among the 5, since 3 are red, this data points become red, which is misclassified. And if we consider this data point, although it is red or it is black, it is nearest to it, these 5 data points, it will also be classified as red. So what about the proximity of the data points? How do we estimate which class it belongs to? So in order to solve this problem, what we can do is we can assign more weights to those that are closer ones. So for example, x bar is this, in this case this is x bar, and we have to estimate where it belongs to. So these two data points that are closer to your x1, they will be assigned a higher weight value, and those data points, the farther away they are from your x1, they will be assigned lower weight values to get better results. So in case of regression, we are not just counting, we are assigning the weights, and then we estimate and we sum the weights of all those points which are red data, among the red data, in case of the nearest neighbor of x bar. So sum up all the weights that are closer to the red in the set of red data, and if your this estimation of the calculation, if s of x bar, it is closer to r, which is the sum of the weights that are closer to r, it is greater than your estimation of blue, then we will say that x bar is in red, otherwise it is in blue. So what we are doing is we are calculating the weights among the red, we are calculating the weights among the blues, and if the weights of the red is greater than weights of the blues, then x bar will belong to r, otherwise b. So we are not just counting, we are putting weight or significance to those data points that are in close proximity to your point under consideration. So in case of regression, we are going to consider not just the averaging, rather we are going to assign the weights, total weights of all the nearest neighbor of x, and then we are going to multiply it by your f of x function, which we will define later. And then this function is dependent on not only the weight values but also the nearest neighbor of x. So what are this distance measure that we can choose? For this w of x that I was saying, that we have to assign the weights that are closer to proximity to the point under consideration, more weights to them. So there are different considerations. As the distance increases, in case of this distance measure, 1 over x into x bar, as the distance increases, so those data points that are closer, their value will be higher. In case of the Gaussian type, we can see we have another distance function that we have defined here, and then we have the another form. So do we need to choose the KNNs in this case? Obviously those data points that are closer to the point under consideration, they will be given higher weightage. So do we still need to consider the KNNs? Yes, we can, but it is not that much required if we are going to use this distance formula. Obviously we are going to give more weights to those neighbors that are closer to the point under consideration. Another is the Gaussian weight function we can use. It depends on all the given data that we have, and we use the kernel regression for or w. Point x, which is among the neighbor, x dash is the point under consideration, and we can estimate the values for this weight values using the Gaussian curve. This x dash is the point that we are considering. What would be the value here for the dependent variable? So it will depend on the value of your proximity function, the weights that are assigned. So in this case, in case of kernel regression, it mainly depends on the value of lambda. If we are considering a lower value of lambda, we will have the CN boundaries or the regression values that are more towards the overfitting. However, if we increase the value of lambda, your decision boundary or your regression line in KNN considers, it becomes more and more linear. So what is the impact of we can see here the impact of different distance measures. So if we are changing the distance measure simply from Euclidean distance to other distance measures, and we are giving weights to those points that are closer to the data point, we can see a different variation of KNN algorithm that is more realistic. So what about the transformations in our data? D2 is a transformed version of your D1. And how is the transformation? Simply what we are doing is, the transformed point is estimated by the point under consideration, and simply you are scaling it by a factor of 2. So this data is being scaled by a factor of 2. And what would be the impact of this decision boundary, you can say? So what about the decision boundary in this case? Will it affect? Let's see. We have two data sets. One is the scaled version of the other. Obviously we have seen that that is linearly scaled, In case of D1, it is more towards the overfitting side, but in case of D2, which is a scaled version of your D1, we can see that the decision boundary is changed. So we have to focus on the other distance measures as well. So the boundary is changing with the change in your representation of your data. So it is sensitive to the distance measure. So choosing the distance measure is an important part of your KNN algorithm. So we can use a generalized Euclidean distance that we have studied, cosine similarities, Pierce correlation, Jaccard similarity. All of these can be applied depending on the situation at hand or the problem domain. So Jaccard similarity can be seen where, or data points, for example, if you are doing clustering, the Jaccard similarity can be used where we can have overlapping. Your points can belong to two clusters. So for that we can use Jaccard similarity. We have already studied the Pearson correlation in previous lectures. So the question here is, can it be applied to only numerical data? KNN? No. So if we define an appropriate distance measure, it can be applied to any type of data. Textual data, numerical, categorical data, sets, other type of data as well. Some of the distance measure we are familiar with. We have the Manhattan distance, which takes the absolute value, Euclidean distance, which is the L2 norm. Then we have LK norm, that is the Minkowski distance. Then we have L infinity norm. So different distance measure can be applied to find the distance between any two points, or the one point and all the other points in the data set. So L2 norm, L1 norm can be represented in this form. If we take the L2 norm, its structure changes. LK norm in this form, which we have defined here for the Euclidean distance. And then we have the L infinity norm, which is graphically represented in the form. So for uncorrelated case, we can use the Mahalanobis distance in a normalized space where we are dividing it by the variance. So we are already familiar with this. I have discussed this approach with you, where you have your data point, you subtract your mean and divide by the variance for the normalization, and your data is represented in a normalized space. So here you can see the transformation this has in the case of normalization.